All right, so last lecture we talked about uh, these rules for aromaticity and in particular being able to classify a molecule as being aromatic, anti-aromatic, or non-aromatic. Probably the most important skill from this chapter is that. But now we're going to focus on molecular orbital diagrams, which is going to be kind of our explanation as to why aromatic compounds are really stable and anti-aromatic compounds are really unstable. Okay, and remember this is an example. This graph here is basically just illustrating that fact that this aromatic benzene ring is remarkably stable compared to what you'd expect, right? We would expect, based on the fact that it has 3 double bonds, that it would release 360 kilojoules of heat when you reduce it to cyclohexane, and in fact, it releases, less than, I don't know, what is that, 60% or something of that. So it is just, take home message here, aromatic compounds are remarkably stable. So why? Okay, so the MO diagrams are going to help explain that. So remember, just like with our conjugated diene molecular orbitals, what we have is that these p orbitals are lined up like that, they can form their own molecular orbitals, okay? And that's where those electrons live. So we're going to learn how to create graphs that look like this, right? When we start out, let's right, we start out, we have our 6 electrons that are in that conjugated benzene ring, right? Each of these double bonds has 2, so that's 2, 4, 6 electrons that are in those p orbitals. And what's going to happen is those p orbitals are going to mix together, and if I have 6 atomic orbitals that are mixing, I'm going to get 6 molecular orbitals out of that. There's always that conservation there. What we're going to see, and we'll learn how to sort of draw these diagrams or why they're drawn the way that they are in a second, but just hear me out. So this would be the molecular orbital diagram for benzene. And then those electrons, we're going to fill this in like we would with when we learned how to do this for atomic orbitals. You start at the bottom, you go 1, 2, every orbital can house 2 electrons. When we go up to the next layer, notice that we have what are called degenerate molecular orbitals, meaning they're at the same energy level. We're going to go through them first, half fill each one, 1, 2, and then 3, 4, or rather, let's say we have 2 already, 3, 4, then go back and fill up 5, 6. Okay, and just like before, when we were talking about conjugated dienes, the fact that the molecular orbitals that are occupied are lower in energy than the p orbitals when they're all by themselves, right? So this is the energy of an electron that's in an isolated p orbital. This is now the energy of those electrons down here and down here when they're in these special molecular orbitals. Okay, so this is an explanation as to why these aromatic compounds are more stable, because they form these really stable molecular orbitals. And if you look at the shape here, it kind of makes sense, especially the base one down here, the lowest energy. That's when all of those p orbitals are of the same phase, so those electrons can just zip around without any problem. Okay, remember, as you go up in energy, there are nodes that are introduced. That's what's being pictured here. We have a node here and a node here. To be honest, that's really complicated, like quantum mechanical explanation as to why there are those nodes. I wouldn't worry about that. Okay, the goal here is to learn how to draw these molecular orbital diagrams. Okay. And what we're going to see is now the anti-aromatics. So let me again. Here is my molecular orbital diagram for cyclobutadiene. And again, why these levels are spaced the way they are, I'll explain that in a second. Let's just make sure that we know, once our orbital diagram is drawn, how do I fill it in with electrons? So first of all, how many electrons do you have to fill it in with? That's the first thing. Well, I have 2 4 electrons that need to be laid down on the board here. I'm going to start at the bottom, 1, 2, and then when I get to the next level, because they're degenerate, meaning that they're same energy, I'm going to have to half fill them first. So that's 3, 4. Okay, and that's all the electrons that I have to put in on my molecular orbital diagram. This is actually an illustration as to why this is an anti-aromatic compound, or I guess more specifically, why anti-aromatic compounds are unstable. And that's because they have, what we'll see is that they always have these half-filled orbitals, okay? This is what's called a paramagnetic electron configuration. Long story short, having only those half-filled orbitals are not stable. It will make this compound more reactive because it wants to fill those orbitals. So it'll either accept or donate electrons easily. Okay, and you can do the same thing with with our other anti-aromatic compound. And again, we'll see that all these anti-aromatic compounds share this feature of having these half-filled. The one thing I'll say is the lecture slides and the images in the book are not correct in the sense that these electrons should be pointed the same way. It's kind of a minor point, but it is important. Okay, so now, well, so I guess this is another fun fact to know about cyclooctatriene, is that because it's, if it was flat, it would be anti-aromatic. It actually distorts its shape in order to have it so that now these p orbitals are no longer sitting in a line, no longer conjugated. This is just a random fun fact about this particular molecule, that it adopts this tube-shaped conformation. Okay, so like I said, the main goal here is going to be to draw those molecular orbital diagrams. And where are those energy levels? How do I draw those? That's what we're going to focus on now. There's this really cool way of doing it, which are called the frost circle method. So what you're going to do is first draw a circle, and then whatever the polygon is of your particular shape. So in this case, we're dealing with, let's see, a 7-membered ring. You're going to inscribe that in your circle, making sure that the point is at the bottom. Okay, so I'll actually do the same thing here for our classic benzene, so we can make sure that everybody gets it. I'm going to cheat and use my shape drawing tool. Right, so if I was going to do it for benzene, the example that's given above is a 7-membered ring. I'll do it below for benzene because we already sort of know the answer for that one. That's going to be a 6-membered ring, and I'm going to have to make sure that the bottom has the point. So this is, you're going to get really good at drawing, not only, everybody's hopefully pretty good at drawing their hexagons from organic chemistry. You're going to get good at drawing all polygons. Now, if I'm going to draw hexane in such a way, cyclohexane in such a way that the point's down, that means it needs to look like this. So that looks messy. The perfectionist in everyone is going to cringe a little bit at this process. Okay, so now step 3, we're going to draw horizontal lines at all of the corners of our polygon, or basically where our polygon meets that circle. So in the 7-membered ring, right, they would put the energy levels here. For our 6-membered ring, our energy levels are here. Whoops. Okay. Now you're going to draw a dotted line through the very center, and that represents the energy. So, right, we have increasing energy. This is the energy of the p orbital alone, or an electron when it's in the p orbital all by itself. That means that this half are our bonding molecular orbitals, the ones that are lower in energy than a p orbital all by itself. And these ones that are above are what we call antibonding, MOs. Okay. So I mean, obviously drawing a hexagon is not too bad. Drawing a heptagon and octagons aren't too bad. Heptagons are pretty hard. Yeah, it's just going to take some practice. Okay, so here's an example of each of the, from 4 to 10. I guess we could also put a 3 over here. Oops, let's use our fancy tool. And here's the dotted line in the middle. Okay, notice that we have, so for each of these now, let's sort of broke it down in terms of how many bonding molecular orbitals that it has. In the case of the 3-membered ring, you have 1. 4-membered ring, you have 1. Notice that these guys sit exactly at that same energy level of a P when it's all by itself. Because it's really hard to draw polygons perfectly, I think actually having these numbers memorized will help you out a lot, right? Because if you, for example, are drawing a membered ring and you don't do it perfectly, then when you draw the line in the middle, maybe some of your orbitals fall below, or some of your molecular orbitals fall below that line. So it's just a good idea to remember that we got 1, 1, then these guys, 5, 6, 7, and 8 all have 3 bonding molecular orbitals, 3 orbitals that sit below that line. Then we get to 9 and 10, those have 5. It's always an odd number. Okay, but having those numbers sort of memorized will help you out, I think. So let's do it from scratch here. So first of all, let's convince ourselves, is this compound aromatic, anti-aromatic, non-aromatic? We did this one, but let's just sort of remember. Indeed, these two are sp2 hybridized, and then carbocations are also sp2 hybridized, so we meet rule 1. There are 2 electrons in that ring, so that follows our 4n plus 2 rule. Series is 2, 6, 10, 14, 18, etc. That follows that rule as well, right? So this is an aromatic compound. And let's see if we can't use those MO diagrams to illustrate why this is nice and stable. First thing we're going to do is we're going to start out with our circle. We're going to inscribe our polygon in it with the point down. So in this case, I'm going to have to draw an upside down triangle. Okay, now we're going to draw the energy levels where those points, where those corners on my polygon are. And remember that this line in the middle is what represents the energy of a p orbital alone, which means that this is my bonding MO. It's pretty messy. And these guys are my anti-bonding. Okay, so now the next step is I got to fill it in with the correct number of electrons. So how many electrons should be in this MO diagram? Remember, if I'm being really good, I have this axis that's labeled energy. Well, there are 2 electrons in this pi bond. So I only have 2 to lay down on my diagram here. So that's 1. I'll use a different color so that it stands out. That's 1, 2. So I have this fully occupied bonding molecular orbital, which is why this is a nice stable compound or aromatic.